Hi, John Hess from FilmmakerIQ.com. Today we'll go over the science of LEDs and cover some of the fundamentals you'll need to wire up these efficient and versatile light sources for your production. The LED, or light-emitting diode, is really quite a marvel of modern technology. The diode itself is the basis for flash memory, which we talked about in our course on data, and the core of every camera, as we discussed in our camera sensor video. But instead of interpreting light like a photodiode, an LED emits light. A diode is basically an electronic component that allows electricity to flow in one direction, but not the other. This is done by exploiting the electrical properties of two different types of semiconductor materials. For a little deeper look at semiconductor chemistry, I recommend checking out our sensor video. We really get deep into it there. But for today's discussion, we'll start with the PN junction diode. Now, a p-type semiconductor is a semiconductor doped with a different element to give the resulting crystal what's called a hole that attracts free-moving electrons. An N-type semiconductor is a semiconductor doped with a different element that results in extra electrons that are free to move throughout the crystal. Both P and N-type semiconductors are neutrally charged. But when we bring them together in a PN junction, the extra electrons move from the N-type to fill the holes of the P-type. They result in what's called a depletion layer. The p-type area, now with its holes filled in with electrons, carries a negative charge because it's got extra electrons, while the n-type area, missing its electrons, has a positive charge. Now, if we hook up a battery to the positive side of the battery to the p-type side and the negative to the n-type side, we can pull electrons out of the depletion layer, making room for electrons from the negative side of the battery. Now current will flow unimpeded through this diode. This is called forward bias. If we reverse the polarity of the battery, we are adding electrons into the diode, which fills the holes and ends up repelling electrons from the battery. The current will not flow in this direction. This is called reverse bias. But how do we get this thing to put out light? Well, let's go back to forward bias. If the electrons from the N-type semiconductor are at a higher energy state than the holes of the P-type semiconductor, and by that I mean they are in a higher electron shell, when they move from the N-type to the P-type, they have to drop an energy state. If the drop is just right, the excess energy is released in the form of a photon, light. But this only works for specific combinations of materials. If we use aluminum gallium arsenide, we get a red photon. If we use aluminum gallium phosphide, we get a green photon. And if we use zinc selenide, we get a blue photon. Now, since this light is really being created at the quantum level, the light itself has a very specific wavelength. With aluminum gallium arsenide, you're really getting pure red, wavelengths of just 610 to 760 nanometers. And that's why LEDs are so efficient. Most of the energy is going into creating light in the visible spectrum instead of going to produce something unwanted like infrared heat. So the big question is, how do we get white light? Now remember that white is not a single color, but a mix of all the colors. We can cheat a little by mixing the three primary additive colors, red, green, and blue. And a lot of LED light fixtures do just that. Another way to create white light is using a similar technique that fluorescent lights use. Take an LED that emits blue or ultraviolet light and shine it into a yellow phosphor-coated lens. This makes the lens glow white. What makes LEDs so attractive for simple electronics is they require very little voltage, but that doesn't mean they are 100% entirely safe. Now, when you start adding a bunch of LEDs together, you could potentially get electric shock, but the voltage to run one or two small LEDs won't hurt you at all. Still, always proceed with caution when doing anything with electricity. First thing, when we're dealing with LEDs, we're dealing with direct current, not alternating current. DC is the power you get from batteries. And if we're tapping into AC power, we'll need to convert that to DC using an LED driver, but we're getting ahead of ourselves. To get an LED to light up, we need to apply a certain amount of DC voltage called the forward voltage for forward bias. Voltage is the electrical potential difference between the positive and negative terminal. Think of it as pressure. A diode needs a certain amount of pressure to pull those electrons out of the holes in the depletion layer in order to allow current to flow through the diode. This forward voltage information is usually available when you buy your LEDs. Generally speaking, red LEDs are 1.8 volts to 2.2 volts. And green, blue, and white LEDs are 3 to 3.4 volts. So let's make a very simple LED circuit. Here I have a watch battery. It's rated for 3 volts. This blue LED has a forward voltage rating of between 3 and 3.4. Now we'll just take this LED and put the longer pin or the anode pin on the positive side of the battery and the shorter pin, the negative or cathode side, on the negative side of the battery. So we'll get that right there. And bingo, we have a LED light. This is about as simple a circuit as you can make. Now LEDs will run lower or higher than their forward voltage recommendation. This red LED, which has a rating of 1.8 to 2.4 volts, will run just fine on this watch battery because the watch battery doesn't have enough current to burn out the bulb. Now it won't run as efficiently without the 22 ohm resistor, which you need to lower the voltage, but more on that in a moment. Now a single LED like this has a rating of about 30 milliamps at 3 volts. So this battery, which is 225 milliamp hours, will run it for hours and hours on end. You can even put more LEDs on this single watch battery, so long as they all have the same forward voltage. See, these 3 have the same forward voltage. Now if we put a red one, we mix up a red one in there, the red one has a lower forward rating, it will hog up the power right away. So only LEDs of the same forward voltage. Now this is a case of running the exact voltage necessary to drive the LED. When we apply more voltage pressure, we get more current, the more electricity flowing through the diode, which results in a brighter LED. Now here's a white LED at 2.5 volts. Watch as I slowly increase it to 3.3 and beyond. Now running LEDs at higher voltages will shorten their lifespan. Keep in mind there isn't really any work being done in an LED. It's not like a light bulb that's heating a filament, where the more electricity you send through that filament, the hotter it gets. In an LED, once the channel is open with the correct forward voltage, electricity just flows through. Increasing the voltage will increase the current exponentially. Increase the voltage enough, and the LED will burn out because there's too much current flowing through that tiny little circuit. Watch as I connect this blue LED, which has a forward voltage about 3 volts, to a 9 volt battery. Yep, that's a dead and gone LED. I wouldn't recommend doing this at home. Now, if you have more voltage than your LED can handle, what you would do is place a resistor on the negative or cathode side of the diode. Resistors resist current in a linear fashion, so small changes in voltage won't cause huge spikes in current and won't totally blow your circuit. To calculate the resistance needed in our 9 volt circuit, we can use Ohm's law. But this isn't the course for engineers. Google LED calculator and you'll find an online resource for determining which resistor you would need. We put in our source voltage, 9 volts, the forward voltage, 3 volts, use a value in the operating range of your LED, and put in the forward current of the LED, 30 milliamps. The calculator will do the math and select the closest commercially available resistor. In our case, it's a 220 ohm, 1/2 watt resistor, and as you can see, it lights up perfectly. But what if we want to add more than one LED, say 3 LEDs to this 9 volt battery circuit? Well, if we wire them up in parallel, that is each one connected to the battery directly, we'll still need to place a resistor on the cathode side of each LED to regulate the current down from 9 volts. Each LED would still pull 3 volts, and the current would add up between the three for a total of 90 milliamps drawn. But if we wire them up in series, that means positive to negative. Instead of adding the current, we add the voltages. So 3 of them together would now have a forward voltage of 9 volts, but still only draw 30 milliamps. We can even mix and match LEDs that have the same current draws but different voltages. Say, take a green and blue LED rated for 3 to 3.3 volts and wire it with a red LED which is only rated for 1.8 to 2.2 volts. Using the high range of the 3 LEDs, together we have a voltage drop of 8.8 volts. The remaining 0.2 volts can be shared among the 3 LEDs, but realistically, not all 9-volt batteries deliver exactly 9 volts. It's usually a little bit lower than that, like 8.6 volts. Now, the proper thing to do, even when you're wiring in series, is to put a resistor at the end of our series. LED series calculators online will suggest a 1 ohm resistor, even if the series voltage matches the source voltage. But for something as simple as a circuit with a battery where we know we have consistent power and we know the battery isn't capable of huge spikes in voltage, I think you can forego that 1 ohm resistor. Now, if you're an electrical engineer building something that's going to be mass produced, that's different. But we're just hooking up small projects for short periods of time, I think you can forego it. Go ahead and crucify me in the comments for saying that. So it's worth mentioning here too that some higher voltage range LEDs already have a resistor wired in, so you don't need to worry about a resistor in those LEDs. So to summarize, to build an LED circuit, you need to know the forward voltage of the LED and you need to match it with your DC power source. Batteries are a good source of portable DC power. Remember, AA and AAA are 1.5 volts, so you'll need to put 2 of them in series to add up to 3 volts. But there are 3-volt watch batteries that work and mini 12-volt batteries that work for some applications. For AC power, there are commercially available LED drivers and all kinds of voltage ratings. If you're near a scrapyard, you can go and try to find an old AC to DC adapter and use those as a power supply. Just make sure you read the specs on the adapter and make sure that meets your circuit requirements. If your LED's forward voltage is lower than your power source, you need a resistor on the cathode side or negative side of the LED. If you're powering LEDs in parallel, the voltage stays the same among the LEDs, but the current adds up. If you're wiring in series, the voltage adds up, but the current stays the same. Well, that's the fundamentals for creating simple LED circuits. Now, let's see what we can do with them. LEDs come in a variety of shapes, sizes, and power draws for different applications. The first application for filmmakers you might think of would be as a light. For this, you'll want to turn to the high power LEDs. These are LEDs rated for 1 watt or above. These little button LEDs, which are available both as warm and cool white, pull 3.3 volts but draw 300 milliamps or so. Multiply volts times amps and we get watts, so it's about 1 watt. I soldered together 4 sets of 4 bulbs each and connected it to a 12-volt LED driver that's 16 watts, pulling a little over 1 amp. Now, these little buggers can create a lot of heat, so I rummaged around a junkyard and bought a used CPU heatsink and cemented the bulbs using heatsink grease glue. Now, these warm white LEDs tend to glow a little bit on the green side, so I attached a piece of minus green gel, which is magenta, and a diffuser on top. For added control, we made this little snoot out of a large can of baked beans and painted the outside black, and mounted everything on a pigeon plate so we could attach it to the knuckle of a C-stand. The fun thing about these LEDs is you can place them wherever you need light and even build interesting shapes out of them. I built this wooden light bar to add some light to the bottom of my green screen, putting 6 of these in series and running off a 20-volt LED driver. Now, each of these is sitting on its own heatsink. Now, since it's illuminating the green screen, I'm not so worried about a green cast from the light. But you can even build really far out there lights. I love the look of long strip softboxes, so I tried to build an even longer strip. I took a 5-foot angled aluminum and smeared heatsink glue down the entire edge, and then laid 15 sets of 8 warm white LEDs. This would run with a 24-volt driver drawing a little over 2 amps. I didn't have a driver handy, so I just used my bench power supply, which allowed me to dim the lights by lowering the voltage, which is really useful but not really portable or practical. Now, a few words about dimming. Dimming LEDs using voltage regulation is the best way to do it, but it's a bit complicated as you need a voltage regulator and a potentiometer. The LED dimmers you see on there on eBay are generally PWM, or pulse width modifier. They don't reduce the voltage but pulse the electricity, flashing the LED on and off really fast so it looks dimmer. Now, that can do screwy things to your camera, so I don't recommend it for lights that need to be on video. My bar light is still a work in progress, and honestly I would not have made it out of aluminum because it's really easy to short if the wires happen to touch the aluminum. LEDs are fun to mess with, but they take a lot of time and effort, and they really don't put out as much light as you think they would. Unless you get those super bright LEDs, which I'm still toying with myself. But these suckers can get really hot. They actually melt the solder that I tried to make the connections with. Honestly, I would much rather prefer to buy an LED light fixture, except for some extreme cases like with my crazy bar light. To me, the real fun of LED is when you get to put them in your scene. What got me started were these LED strips. These 50/50 RGB LED strips run off of 12-volt power and are controlled with a little box here and a remote control. They come with adhesive backs so you can attach them for accent lighting here and there on your set. But there's really more creative things you can do. I wired these up in rows and placed a styrofoam hemisphere on top and put a bunch of fiber optic cable to create a glowing centerpiece. Then I got a little crazy and peeled off the waterproof coating and cut out the LED from the 50/50 strip and soldered 2 poles to each side of the LED. The blue and the green will light up just fine at 3 volts. I hot glued the LED to a bunch of fiber optic wire, wrapped it up in heat shrink, although electric tape works too, and attached a 3-volt watch battery and glued everything to a hair clip for this multicolored fiber optic hair clip. But why stop at a hair clip? I took this Victorian hat and added some fiber optic, again using a 3-volt watch battery and a couple multicolored LEDs I cut out of a 50/50 strip. And I created this glowing Victorian hat. But why stop at a hat? I wired red, white, and blue LEDs to a 9-volt battery on this corset. I even used LEDs to drive the side glow fiber optic. The end result is every light you see in this scene comes from the quantum dance happening inside each LED. The light from the left is my bar light, from the right is my 16-element snoot light, the background lights, the costume, all entirely generated by electrons falling from higher to lower energy states. Physics has never been so sexy. LEDs have kind of become an obsession of mine. The possibilities are endless. You can use them to drive fiber optic to create little miniature lights in your models for miniatures like miniature starships. You can use them to create little LED light painting tools like this little blue brush, or even this big LED wand. Looks sort of like a lightsaber. I used this on a recent photo shoot to create some really cool results. Now, my costume design capabilities aren't that great, but I created this little side glow LED swimsuit that I think looks pretty cool. But the pros working on the failed 1997 Superman Lives by Tim Burton created this full-fledged programmed LED fiber optic suit that would have been really cool had it not been completely out of canon. There are so many cool things you can do with LEDs. I hope I piqued your interest and given you a base level understanding of how they work and how circuits work. So next time you're watching a DIY tutorial on LEDs, you'll have a basic understanding of why they're doing what they're doing. But remember, you are working with electricity, so use common sense and stay safe. Go out there, experiment with LEDs, and make something great. I'm John Hess. I'll see you at filmmakeriq.com.